In this video, I'll be going over how to do logistic regression classification using scikit-learn. I'll also be walking through some various features within the scikit-learn library. So to begin, I will first talk about scikit-learn. So scikit-learn is basically a Python package that offers a consistent interface for all sorts of machine learning, supervised and unsupervised learning models. You can do a variety of things from like classification, regression, model selection, pre-processing. Today, we'll walk through a quick overview of various machine learning model steps, and then from there, we'll use those steps to train a logistic regression model using the iris dataset. So first of all, the first step in any machine learning model building is to first understand the data. So you want to create graphs, make visualizations, any way to understand what exactly is the distribution of these values within each of your columns in your feature data set. The next step is to pre-process. So this involves scaling or identifying if there's categorical or like continuous value variables in your features. Next step is to build the model. So this would be to actually split the data into your training set and test set, and then from there apply a variety of machine learning models, including random forest, SVMs, regression, and these types of models are all found in the scikit-learn library, so they're easy to use, and they all have the same methods we can call to use them. So it's very nice and it's very consistent, and we can apply these models by just switching a few basic words in each of the functions. So that's the building the model. The next part is testing and iteration. So this involves now actually comparing different models and then finding out which one works the best. So that's an overview of the machine learning model steps. Next, we'll go into the iris classification problems. So the goal here is we have three different types of irises. We have these types here, and then we want to use the sepal, which is this part of the flower here. We want to use the width and the length to predict the type of flower. So there's also like the petal size here, but we're going to focus on two variables as features, and they're going to just be the sepal length and width. So with that, we'll begin. So we're going to read in this data set. I have this in the same directory as this Jupyter Notebook file, so I'm going to read that in. And here's a preview of what the data frame looks like. We have the length and the width here. Then we have the type of flower. I'm just going to do a quick check. So how many types of each flower exist? We have 50 of each type of flower. Then we're going to shuffle the data. So shuffling data is important because you want to make sure when we split this into our test and training set that there is, all three types of flowers are in the training set and test set. So we can basically build our model knowing that all three types of flowers exist. Next, we're going to check for NA values. There's no NA values, which is good, so we can skip that. We can move on. Next, we're going to split into the X and Y vectors. So the X vector is the features we're going to use to make our prediction, and then the Y is our labels. We have that here. You can see here, we just simply split. I used the iloc method here, and I just took this column, and that became our labels. Next, we're going to map to features, or map the class labels to features. So these are the names of the flowers here. I'm going to map them to an integer. So you can see that I just did the simple mapping. I just passed in a dictionary. Next, this is an important part of understanding the data. I want to visualize the feature distributions. And this is pretty much to get an idea of how the sepal length and sepal width, what do these different features look like? So here I just did the distribution of the sepal length and sepal width. So it's it's good that we have some type of characteristic. It's not just like random data here, so it's good. And we see there's some type of normal-ish shape distribution for the sepal width and sepal length. So next, this is important. I've broken up the sepal length and sepal width distribution by the type or the species of flower. So the first row here, this is setosa, and then this is versicolor, and so on. But you can see here that there is a slight difference between the flower types, right? For example, for the virginica flower here, we see that on average, the sepal length is a bit longer than the versicolor and setosa, right? So this is important because it's showing us that the sepal length and even the sepal width are factors that we can use to predict the type of flower, because each flower is a slightly different distribution of sepal length and sepal width. So that kind of validates that our model will actually be useful, and we can actually use these two factors to predict. And that's a good sanity check to do whenever you're building a model, to check that the data is not just random noise and there is some underlying distribution you can rely on. So next, we're going to build the logistic regression model. You have a training set, a test set, and a validation set. So very quickly, the test set is what you're going to do to, at the very end, to basically see if how your model actually performed on, this is like the data it's never seen before. The training set and validation set, this is the data we're going to use to build models. So we're going to build a variety of models using our training set and then see how these models perform in the validation set. And then if that first model maybe wasn't too good, we're going to build another model using the training set again and then test on the validation set. So we're going to use this multiple times, go back and forth between here. And then once we find the best model using this part of the data, we're going to go and make our final prediction on our test set. But the idea is you don't want to use a test set too early because then you've basically corrupted it, you used it up and you can't use it anymore because you've already predicted on it. So you save the test set to the very end when you're confident that your model you have is the best it can be. So in this model, in this example here, I'm just building one logistic regression model. So I'm not going to actually build a validation set because I'm only building one type of model. If I was to build multiple models, then I would want to use a validation set. So it's great that scikit-learn has a method for doing a training test set split. So we can split it here. Right now I'm splitting it to 20%. So 20% of the data will go into our test set. I can just do a quick sanity check to see how many samples are in each in the training set and test set. Okay, and then now I'm going to be building the model. So in the lecture slides, I talked about how to what the mathematics behind the logistic regression, and now it's just implementing that. So scikit-learn has a nice interface. You can just basically use this to build the linear regression or the linear logistic regression model, and then you can pass in a parameter to tell you the type of multi-class model you want to build. So if you remember from the slides, there's two types of multi-class models. Well, first of all, this is a multi-class problem because we have 3 types of flowers, so it's not like a binary case. There's 3 flowers. We need to use the multi-class model, and there's 2 types. There's the when versus rest, and there's a softmax regression. They might be pretty similar in practice, but you can just input the type that you want to use. You can check them both, but I'm just going to use the multinomial here. So I'm just passing in multinomial as to the multi-class function parameter here. And this initializes our logistic regression model here. And now I can use that to fit it to the data. So I'm fitting it here. And then next part, I'm going to get the training accuracy. Again, this is basically saying, this is the data that the model was built with. Now let's see how good it is on the actual data that it was built with. And I get a training accuracy of about 83%. So not bad, yeah. So now I'm going to look at how this error is calculated, how this accuracy is calculated. So the idea here is, you can take a look at this function on your own time, but the idea here is that if the labels match, the actual label matches the predictor label, I give it an error of 1. If the label does not match the actual label, for example, in this case here, over here, I give it an error of 1. And what I do here is I have this column that keeps track of the error. And then I get the error rate, which is the average of this column here. And then I do 1 minus the error rate to get the accuracy. So that's the 83% that we calculate here manually, and it's also the 83% we saw here. So that's the intuitive way behind how the logistic regression is calculating error. So error is great, but so next we're going to look at that was error on the training set. So that was the data that the model saw to build the model. Now we want to test and get the error or the accuracy on the unseen data, which is the test data. So now I run that and I get a 66%. So what this means is that it performs a little bit worse on the training data or on the test data. And this makes sense because it hasn't seen this data before, so we'd expect it to not be as good. So accuracy is one measurement, which we've seen here, but it's also important to look at other measurements that look at where are the incorrect predictions, right? So in this case, we can classify all our predictions into 4 types. We have true positive, which is a type of prediction where the predicted label matches, we predicted positive and then the actual label is positive, so it's a correct classification. True negative is when we predict a negative and then the true label is negative, so it's correct again. We have false positive, where we predict positive, but the actual label is negative. So in this case, we're wrong. And then for false negative, we predict negative, but the actual label is positive. So in this case, we're also wrong. So the idea is you want a high true positive and true negative rate, right? Because that's the ideal. Those are the ones where you actually predicted correctly. And that's exactly what accuracy is doing here. Accuracy is essentially measuring the true positives plus the true negatives over all observations, right? And that's what we calculated earlier here. Next, we're going to talk, the next type of a metric you might use to evaluate a classification model is called precision. And the precision model looks at the number of correctly classified positive observations out of all observations that were predicted positive. So what this means is we have, there's some set of things of observations that we predict positive, and how many of those were actually correctly labeled positive. The next type of metric we'll talk about is called recall, and this measures the number of correctly classified positive observations out of all observations that are actually positive. So in this case, we're looking at the number of correctly classified out of the ones that were predicted positive. In this case, we're looking at the number of correctly classified positive observations out of all the observations that were actually positive. So slightly different denominators here, but they have kind of similar meaning, and you would want both of these to be high, right? Because both of them high would indicate that your model is performing pretty well. So we can use this Python metric, basically the scikit-learn has a library we can import here. We can just check metrics, and metrics will allow us to see the precision and recall for the different types of flowers here. So it's very quick for us to see. And then there's also a different method here. We can look at, this prints it out, so you can't really index in here and get these values, but here we can actually, like if you want to take this value, you can take it here. So it's printing out as an array. So that's just another way to get the same data, the same calculation. We can organize these 4 true positive, true negatives, these values here into something called a confusion matrix. That's what's going on right here. It just takes the predicted positive, actually positive, and puts the value true positive here. So it's a nice way to visualize, what is your true positive and what is your false positive and different types of classification errors. And obviously along the diagonal, it's the ones that are actually, predicted correctly. So there's different ways to do that. One way is to use this function here, this confusion matrix function method here, and then pass it here. You can also use this this plot confusion matrix method, and then you can get this kind of nice visual shape here, visual way, and then you can check, along the axis, if this is really high, which it should be, then you have a decently good logistic regression or classification model. And one thing is, this is a newer method, so it's found in a newer version of scikit-learn. If you have an older scikit-learn, this won't work, so make sure you update scikit-learn, and you should get this this method here. Next, we're going to talk about visualizing the results. So we are making classifications, and then the idea is some of them are going to be wrong, right? So where are these wrong, and where are the wrong ones happening? Well, we're going to make a quick plot to show you how that happens. I'm going to skip the code here because this is more something you might learn in the visualization module. But the overall idea is that essentially we're using two features to predict the type of flower, right? We're using the sepal width and sepal length. So if I take every single combination of sepal length and sepal width, all these different combinations of values in this grid, I can throw them into our classification model and then get an output, right? A prediction. So that's what I've done here for every single basic coordinate pair between the sepal length range and the sepal width range. I found every single coordinate pair and I passed into the function and I got a classification, and then I basically apply these classifications now. So I get this type of this boundaries here, right? Anything, and this is going to be a one type of flower, another type of flower will be here. And what I can do is I can go over here and I can plot our the different predictions. So this is the actual labels. So you can see here that these are the actual labels for our irises and our training set. Our model is doing pretty well, right? It's training these boundaries, and you can see that most of the blue ones are in this region, most of the brown ones are here, most of the yellow ones are in this region here. And of course, this is nature, right? So it's not exactly that, if it's between this length, it has to be this type of flower. There's always some variation in nature. That's how we see some points over here. And these are this type of flower, but they have a kind of an odd outlier type of sepal length, right? Or yeah, the odd outlier type of sepal length and sepal width pair, right? So they're appearing on this side in this region, but it's pretty good, as we can see here. And this is the actual predicted label, right? Because anything that falls within the boundary here is going to be predicted that color. So you can see here that it's these values here and then a few of these here that were predicted incorrectly. But overall, our model is doing pretty well. And this is a training set. Now we can look at the test set. So obviously test set, there's gonna be less data because it's only 20% of our data set. But you can see here that it does have some issues with these yellow dots are being predicted incorrectly. But in general, we have quite a bit of the the blue dots are captured here, and it's doing relatively good. But the main idea here is if you have something that's like simple and you have only 2 features, you can visualize your classification model this way. So next, we're going to talk about feature scaling. So what you can do is sometimes you have these distributions of your features that are very skewed, right? You have one feature might be in the millions range, and one might be just in the 0.00 something. So it might be these very different scales. And the idea is you want to scale them so they're similar. They're similar. So there's 2 types of scaling you can do with the scikit-learn. One is called min-max scaler, and this basically takes all your values in a column and pushes them into the 0 to 1 range. So it makes the maximum value become 1, and then the minimum value becomes 0, and then everything else is kind of pushed somewhere in between. And it does not like change the scaling of it, keeps them the same, but just kind of pushes it so everything fits in the 0 to 1 range. And that's what's happening behind the scenes to get the code, but you can just simply use this, and I'll show you how in a minute. The next one is standard scalar. So from probability, you've probably heard of the standard normal, which basically is a normal distribution with a mean of 0 and standard deviation 1. And you get this by just taking your data point and minusing the average and then divided by the standard deviation, right? So this is what we're doing. We're going to make the whole column have a mean of 0 and standard deviation of 1. And so here's what I do. I just take this scikit-learn.preprocess, import the scalar type here, and then I call this. Then I use these Friday steps here to transform it, and then I'm just passing in the x features, and I'm going to get a new x feature with the scaled x features right here. And then I can just quickly check that because I'm using the standard scalar, I should have mean of 0, standard deviation of 1. And as you can see here, yeah, the mean is pretty much 0. It's really small here. And then the standard deviation is pretty much 1, right? So we are good to go there. And then we can just, of course, use the same set of, we're going to split the data, then we're going to split the data, then we're going to, split the data, train it again, and then build your model and get the test and training accuracy. And here, as you can see, I just passed in the new scaled data. So as you can see here, our test accuracy it didn't really change. It's 0.82, so it's pretty similar. It didn't really change because, as you can see here, the distribution we had of our sepal width and sepal length were not super different. So scaling did not have a big effect, and the test accuracy didn't really go up that much either. So it wasn't a big effect, but in some cases you will see a big change when you scale it. So it's important. Extra feature we can do, an extra step that might help your model. So that's it for logistic regression demo here. Thank you.